have a base in China. Yeah.
So sorry for being late, but it has been exercise for me to find the right building. I had a different labeling. Okay, so welcome to this session, right? So I'm supposed to discuss a little bit about modeling with you. And most of the time when I mention the word modeling, half of the meeting room is just getting empty, and the half is actually remaining because they don't have the time to escape. Huh? So I'm just going to try to keep it as lively as possible. And I did also my best to remove all the math out of it, because to me, I mean, if you want to understand what modeling can do to help you to understand fundamentals about materials, ideally you should be able to explain it without having too many equations, right? So I count on you to let me know if I did the job at the end, so that I can at least improve for next time for your successors, right? Okay, so what is this all about? Point is that with the development of new materials and new technologies for transistors or for memories, we need more and more to deal with very complex materials. As I will explain it later on in this presentation, we start introducing a lot of crazy components. We have ternary components, quaternary components, and then all of these new materials sometimes, but they have to be compliant with a set of requirements. Quality of the materials, of course you need to grow it. Huh? You need to make sure that there is no impurities, that you have everything under control, that you control all type of interface, and then ideally that you have some insight in all what could go wrong. And that's typically where modeling hopefully can help you a little bit to get some understanding on what could go wrong with all these materials. So to try to illustrate my point, I pick up a few cases that I hope will be interesting for you. But before we dig into that, I mean, I don't know, have you already had the opportunity to visit IMEC? You have some idea on how it looks like? Okay, I took a few pictures for you so that you have some idea, huh? Some flavor. So, I'm sure you all passed in front of the building, right? Huh? You have this big tower, which is actually here. Huh? But I mean, there is no way to miss it, right? Because I mean, that's really one of the highest building you find in the neighborhood. Huh? This is basically what we call the IMEC tower. These are mainly offices. But actually, all what you see here, and okay, I'm sorry, someone here, actually corresponds to what we called our pilot line. So the pilot line is actually the place where basically all my colleagues are going to carry on the experience. Meaning, what kind of experience? Well, actually, we are working on silicon wafers, and the diameter of the silicon wafers is actually a technological reference that we are using. So typically, people have been using over the last 2 decades 20 centimeter wafers, something like this, and then they went to 30 centimeter. So you will tell me, who cares, right? 10 centimeter extra or less. Well, actually, to make this transition from 20 to 30 centimeter, we typically had an investment of €500 million. Okay, that's huge. And actually, the requirements in terms of technology and in terms of materials that you need to deposit in the system are completely different. So even the infrastructure that we have in our 200 millimeter pilot line is completely different here. Just to give you an idea, I mean, just the height of the ceiling has to be 2.5 meters higher. Why? Because most of the tools that we are using are getting larger and larger, and they don't fit anymore. That's stupid as it sounds, right? Bon. So we have some extensions also, actually, where we can carry on more exploratory device concepts, more exploratory exercise in terms of material depositions and characterizations. So what I'm going to talk about today are actually part of the work which is done here, but also there. Bon. So just to give you an idea, I mean, IMEC, for those who actually don't really know what it is, we have about, and I'm sorry, the numbers are not necessarily updated anymore, because each year it keeps on increasing, and I've been a little bit lazy preparing this lesson here, because actually we are now 2,800, and we have about 78 nationalities. So the working language is of course English, right? So what we try to do is actually we try to position ourselves between, say, the fundamentals we try to observe at universities, concept of devices, and actually what the industry needs. To give you an idea, next week I will visit Sony and Samsung to give a report on the modeling activities we have, because we help them understanding fundamentals problems in device, but also in material structures. So how does it look like? Well, I mean, if you are lucky, if you can step in, you will see a lot of people walking around in white suits like this. Why? Because our pilot line has to be, the environment of the pilot line has to be an extremely well controlled environment. So the humidity, the temperature, but also all the vibrations coming from the highway, everything has to be under control. Why? Because we are dealing with objects that are typically the size of today, something around 2 times the width of a DNA strand. Okay? I mean, I find it amazing that you can do this kind of small objects, controlling the chemistry, controlling all what could go wrong there at the dimensions of 2 times the width of a DNA strand. So for this, we need to develop a lot of techniques. We need to develop techniques that allow us not only to deposit the materials, but also to etch them, because we need to make pattern, to clean them, and all of this at the tiny dimensions. Okay, so what is the driving there? Well, actually, the driving is that this is getting so much complex in the system that most of the companies in the world decided to put all their money in a joint research fund. And that's basically what IMED is doing today, actually understanding the fundamentals of all those new materials and all those new devices in such a way that they could all get the fundamental understanding, extract it, and go for productions. I'm sure you all get these things here, right? Don't tell me no, because I won't believe you, right? Do you know that in technology developed by Samsung, the memory has been developed in IMEC, half of the processor, half of the display, and a part of the battery? No. That's cool, I like it very much. So, okay, well, that's why I'm here to sell it, right? So, okay, well, what is this about? Well, as you know, when we started working in the field of transistor, all of that boiled down towards the first invention of the transistor. I don't know if you have already seen the very first transistor that was made, was germanium made. And this is a very beautiful germanium crystal with 2 crocodile clips on top of that. And then people say, hurry, we measure something, current off, current on. Today it looks a little bit simplistic, but actually it went a long way from the invention in the Bell Labs in 1947 to what we actually know today. Today, I mean, okay, stop here. I should really expand my more slow, because we are around, I think, that 6 billion transistors on a centimeter square. Okay. So just to give you an idea, that would probably mean that we need to fit, if you take a meeting room, which is probably like 10 times this size, if we project ourselves with the first development of the first transistor, which was the first chipset where people were using 2,300 transistors, so that would still fit more or less in a room which would be 10 times this size. But today, keeping the size of the room fixed, that would actually require that we would be fitting about 1.6 billion of people in the same room. So we can be very creative, right? Stacking people like this or like that. There is no way that we can achieve this aside from reducing the dimensions of the people in this case. So be ready to be shrunk down, because that's basically the trick that you are going to take today. Okay. So in order to be able to achieve this, well, we have been scaling the dimension of the transistor as much as we could. Okay. So this basically gave you some kind of top-down approaches through time, where basically, as you can see over there, the dimension of the active component that we call the transistor has been shrunk as much as we could. So today, if you project yourself, we are around 2 to 3 nanometer, which is between from 1 to 2 times the width of a DNA structure. But in order to be able to do this, we had to replace this transistor, where you see these crocodile clips and this single crystal, by something which was actually controlled in terms of material deposition. So what did we do? Well, basically we've been working on all what could be changed in the transistor. So I don't know, are you all familiar on how a transistor is working? Don't be afraid to say no, if that's not the case. Yes, no? Maybe? Half and half? Okay. Well. So in the transistor, what do you have? You have a source, a drain, channel. You have a dielectric, which is preventing the current which is flowing from the source to your drain to leak away. So this dielectric normally has to be as resilient as possible to avoid what we call a leakage current occurring in the system. And on top of this, we have a gate, which basically allows us to control the electron flow from the source to the drain. So in order to have this working, we basically have been replacing all what could be possible in this transistor. In the early 70s, everything was made of silicon. It was silicon here, silicon oxide, silicon. Now today you have silicon germanium. It depends a bit on the technology you're interested in. It's again silicon germanium, but with a different concentration of germanium. Then your dielectric is hafnium oxide. Then your metal gate is typically titanium nitride or tantalum nitride. Now we are replacing the metal gate by other compounds. So typically now you start finding different compositions in that gate. So sometimes a small layer of aluminum, or sometimes a little bit of tantalum nitride coated with titanium nitride. And now we try to replace this by new concept of devices. Why? Because if we need to keep on sustaining the development of electronic and low power electronic, because you probably, I hope you're all aware that all the laptops and our cell phones are actually increasing our requirement in terms of electricity consumption. And we know we have a certain amount of electricity available that we will be able to produce. So if we don't need to build a second sun to power it, we need to reduce the consumption. And today we are building new type of architectures, being either carbon nanotubes or 2D materials, or what we call spin devices, in order to reduce the operation, the consumption of energy per computer operation. But this is another story that might be for another time. All of this is actually possible if you know your chemistry and your physics and all the materials in the system. So you need to be able to understand how the materials are interacting at each step of these devices. And believe me, probably 60 to 70% of the population of IMEC are chemists or physicists, or they are at least doing material engineering. Okay? Why? Because all of this is bound on that. So you need to understand a little bit how the chemistry is evolving in the system, and for this also modeling is actually helping you a lot. So in terms of trying to give you a flavor of what modeling can do in the system, I did my best to put here the scale, where basically these dimensions give you the time scale that you can simulate, okay, hours to femtoseconds. And then this is the dimensions of the object that you're able to simulate. So what do I mean by this? So this object that you see over there, here, is one of the tiny transistor, one of this 2 to 3 billion of transistor you get on your centimeter square. This normally you can model using techniques that we call finite element modeling. So this is exactly the same kind of technique that you will model, that we'll use to model this building or the mechanical rigidity of a bridge. Of course, if you are in dimensions where you're only dealing with a few nanometers, one can really challenge the application of such a very macroscopic formalism that they could describe say bricks and mortar and cement in the system. Because at tiny scales, so around the nanometer scales here, probably the approximations we do here, they don't hold to be true anymore. So what we try to do is we then to try to improve gradually the description of what you can go. If you set yourself on the other side of the spectrum, so you only have a few atoms, 2 times the width of a DNA strand, that's only a few atoms, right? So then, okay, you cannot escape quantum mechanics, like it or not. That's basically what I'm doing every day. And also this techniques that basically we are using is called an atomistic technique. That is to say that you are taking explicitly for the contribution of atoms. And in tiny dimensions, they are deciding of everything. A device today is 85% of interface. So all the interface between the atoms, the type of bonds, is defining how your device is going to operate, all the chemistry, and how you are going to deposit them. So we are going to discuss a little bit about what these techniques can give you. The purpose of this lesson is just to give you a flavor. I'm not going to make expert of you with this modeling technique. Would you be interested? I can come back. I have about 30 hours of quantum mechanics that I can give you. I see that nobody is willing to volunteering. That's okay. I will just go for the short lesson. So in practice, if you go in tiny dimensions, the simulation time of what you need to model is actually almost exploding. The smaller you go, the more complex actually the physics of your system. So you need to actually try to solve Schrödinger equations in such a way that you can get information about the electronic structure and the energy of your system. So what kind of information can you get out of this whenever you can do this properly? Well, you can get a lot of material-related informations. So first is basically you can get information about the morphology of your materials, the crystalline structure or the amorphous phase. Why is this important? Because sometimes we are looking for new materials that have specific properties. So when you build a transistor that looks like this, and I will come back afterwards, you typically need to be able to connect your transistor. That's basically what we call the interconnect layer. That's a metal layer that we typically deposit at a nanometer scale. And now more and more we try to replace these metals, which is actually built from copper, with something which is better. But in order to do that, you need to be able to identify the most relevant crystalline phase that could exist for a metal or for a given alloy. And not everything is tabulated in database, so you need to be able to calculate this. Once you know this, then you can get a lot of information about the chemistry of the system. So for instance, activation energies of chemical reactions. Okay? So there's a kinetic of the system. But also the thermodynamics. For instance, if I put oxygen together with copper, will I get copper oxide or not in the working conditions I'm dealing with. You can also get, of course, the electronic properties of the system. If you want to replace a metal or a semiconductor by a new one, you need to make sure that at least there is an added value. So the electric gap, the effective mass, the band structure, all of this should be predicted beforehand. Then aside from that, because I told you, these devices are actually built of a lot of different interfaces. One here, one there, one over there, with one with the I tray, the I gate, the metal gate, the interconnect, the locate, you get the system, the dopants. All of this is made of interfaces. So getting insight into how the interfaces are going to impact on the operation of your devices is actually very important. So then getting information about interfacial properties, electrostatic, work functions, XPS, UPS data, because these are indirect ways to quantify. This is extremely important. Aside from that, you can get a lot of information about physical characterization technique. Because you know, most of the time, what happens is that you measure the film that you deposit, and then you have no clue of what's going on. We have a set of database of spectra to compare to, but if there is something exotic that happens during the deposition of the material or during its integration, then you're lost. And this techniques actually helps you building scenario, trying to understand, if I get a little bit of oxidation in my system, what am I expected to see in terms of infrared or XPS spectra? So this simulation actually can help you getting some insight in the system. We're spending also a lot of time in trying to understand the mechanical properties of a system. Why? Because again, project yourself in tiny dimensions here. If you have 5 nanometers of width, and if you start building on top of that layers and layers and layers of materials, you can be the strongest man on the world. I mean, you will collapse, right? Because you are not strong enough to withstand the mechanical strain which is present in the system. It's a bit like building an inverted pyramids. Huh? Usually you don't want to be the one holding the pillar at the end, at the ground of the system. So you need to be able to find in the system the right mechanical properties of the system. So we have a long list of spectra we can simulate, but also, very importantly, we can go for a virtual screening of materials, being able to identify the right material for the right problem. So coming back to this kind of structures, I made here a sketch of where basically my team has been involved in trying to understand the fundamentals of properties of an interface. So we are studying actually, so this is your transistor, you see here. What we call STI is a silicon oxide. This is silicon or silicon germanium with different composition. You get the metal gate on top of this, which allows you to control the device electrostatic. And you need to be able to contact your transistor with the metal pillars. And these are different layers. It's basically what we call metal layer 1, 2, 3, 4, 5, and it goes up to sometimes up to 10 on top of this. And these metal layers, they are actually, you don't see it on this plot, but all of this is surrounded by what we call a low K dielectric, which will prevent us from having this pillar speaking to this one. So when you go for the deposition and identification of new materials, you need to be able to understand the fundamental of the deposition. The dimension of the object is a few nanometer width, so that's very challenging to be able to deposit the material up to the end in a conformal way, so following the morphology of the system, filling it completely, and controlling the grain size, which is extremely important in the system. So for this, sometimes we need to dig a hole in the system, so we need to etch, and then we need to put water inside. So water has to diffuse inside to clean up, and then you need to remove it, so which is extremely challenging here. So there, atomistic simulation, you can give you a hand on what's going on, to understand what's going on. You can also understand the fundamental of the contact resistance. How do you dope your system? How do you control your interface electrostatics? If you grow materials in your transistor, you also want to make sure that it's defect-free, that you are also have good control of the doping profile which is present in your system. If you want to replace it, again, what kind of materials? How do you control all the interactions around it? And this is only for a transistor. We can do exactly the same exercise for all type of prototyping memories which are present. So some of them are magnetic based, that's what we call magnetic tunneling junctions, or memory shift based, where basically we're going to make the life of the electric completely miserable. We're going to destroy it, and we're going to use this operation to make a memory. I have an example later on. Or flash memories. These are actually the flash card you have on your cell phone, perhaps even in your laptop if you have an SSD disk. These are made of flash memories there. So you can understand a lot of the fundamentals present there in terms of materials, and also for displays and batteries. Okay, so that was the appetizer, right? Now the main dish. How do we do that? Well, basically, what we do is we try to solve the Schrödinger equation. I'm not going to give you a course on quantum mechanics, but I will just give you a flavor of what we try to do. I'm sure you all know that solving the Schrödinger equation for a system that has more than one electron is extremely challenging. You need big supercomputer if you have 2 electrons. And I'm going to do this for a system that has perhaps 60,000 or 16 million of atoms. So of course I need to simplify a little bit the problem. So what do we have? Well, when we deal with atoms, we are dealing with a lot of different things. We have particles in movement, right? So we have electrons, this point here, and we have nuclei. Because there are movements, they have a kinetic energy for the electrons and the kinetic energy for the nucleus, right? Well, aside from that, because they are charged particles, they are interacting together. So you have a term that describes the electrostatic interactions between the electron and the nucleus, this part here, the electron and electron together, and nuclei together. So the trick that we are using in order to approximate this solution for a system that has a lot of electrons consists into the fact that we are making an average of the interactions between the electrons themselves. And I'm not going to go over more in details. If you're interested, no problem. I can organize special lessons for you. I make for about 10 hours. I like it very much. So do me that favor. If you ever come to IMEC, if you want to register to that part, I will give it with a lot of pleasure. But basically, what we do is we need actually to simplify a little bit the problem. So we have a look to these interactions between the electrons together. Okay, and because we simplify the interactions between the electron by an average one, we are going to introduce mistakes there. tiny mistakes. It's about 1 to 2% of the reality. But this 1 to 2% of reality is actually generating a lot of problems in what we want to achieve. Why? Because all of this is generating a lot of problems in my field. So to give you an idea, if you use this technique, using what we call density functional theory, that's another way for this atomistic technique, another word for this atomistic technique. Well, basically, you get your band gap, so the electronic gap in your materials, which is wrong. So for instance, this technique will tell you that silicon has a band gap of 0.6 eV, while in reality that's 1.2 eV. Germanium is a metal in this technique. Well, in practice we know that's a semiconductor, right? So all of this is qualitative, right? And we can improve on the quality of what we do. And I'm not going to go much in details. I will just show you the kind of qualitative insight that you can get, provided that you know how to correct your data, okay? So you can actually get more quantitative descriptions in your system, and then in that case you typically are between 5 to 10% of what you're measuring experimentally. In my field, 5 to 10% of deviation is extremely good. Okay? In your field, probably not. Huh? The deviation of 10% in your ranking is probably not what you want, but for me it's completely good enough to actually get information about chemistry and physics. So how long does it take? Well, actually, it depends a little bit on the kind of techniques you are going to use. So normally, all these simulations that we call ab initio also. So ab initio means in Latin from the beginning. So you solve all the Schrödinger equations, approximations, without using any experimental data to be able to solve it. So if you plot your CPU time versus the dimension of the system you want to simulate, so typically what you have a box. You put the atom inside, and then depending on the number of atoms we put in the system, so this box is repeated periodically in the 3 dimensions, while the simulation time will be either long or short. So typically today we work with dimensions of this box that range between 100 to 200 atoms. And as you can see over there, it takes around 2 days per simulations. To give you an idea, if you are looking for new materials, you need sometimes to scan something between 10 to 20,000 simulations. Okay, multiply it by 2. I mean, you're not even at the end of your PhD that you have seen you have seen your results. So of course you need a lot of computational power, and that's basically what we have built in IME. So there are different types of techniques. So most of the techniques scale up to the cube, and n is the number of atoms. So whenever you start simulating something, you better have to think twice before you push the button start, because it takes a little bit of time. Okay, so what do you get out of that? So I already told you the list before, so I'm not going to review them, but I will just give you some idea about the accuracy. So I'm sorry, I don't know why. When I made a copy paste, I mean this is slightly shifted. So I mean this point corresponds to this one, the thermodynamic corresponds to this one. Okay, so that's slightly shifted. So in terms of structure and morphology, if you're interested by identifying new materials, crystal structure, you're typically between plus minus 1 to 3% of lattice constant. You can even compare X-ray pattern directly with these simulations. If you're interested by thermodynamic quantities and kinetics, you're between around 0.1%, 0.1 EV, of deviations, which is extremely good. So already by using this, you can say, look, if I'm using material A, B, C, and D, and I'm exposing this to an H chemistry, or I want to put nitrogen in contact with that, this will tell you it will react or it won't react. You can get information about infrared measurements, and there typically the deviations vary between 1 to 20 centimeter minus 1. It's extremely good. So we are now using actually these techniques here to sustain one of the new research lab we are building in IME, what we call the ATO lab. So the idea is actually to study the chemistry and the physics of materials upon extreme EUV degradations. So the EUV is one of the lithography steps we are using to make a pattern in the morphology, and there basically we're bombarding materials with an energy which is 94 EV. It's a bit like shooting bullets directly on a sheet of paper. Everything goes straight, and then you get a lot of chemical modifications of your materials. So the band gap, that's basically the weak point of this technique. You're typically very bad. Best you get 60% off. Germanium is 100% off. Most of the time in all the oxide you're around 50 to 60% of deviations. You can get around 95% of the experimental value, but you need a lot of computers. Dimensions, typically you can model system up to 150 to 200 atoms. And then the simulation times actually depends a little bit on what you're interested in, but sometimes it spans from hours to months. So we use all of that to basically understand the fundamentals of materials and process development. I will illustrate my point. I will try to explain how we failed several times in IMEC to build a germanium transistor. Remember, I don't know if you pay attention to what I said at the beginning, but the very first transistor ever that was made was germanium built, right? And it took us at least 15 years to figure out how to build it back at the 5 nanometer dimensions. I will show you part of the misery we've been having. So, okay. So why do we need germanium? Or eventually 3.5? Well, simply because, I mean, as you see, you're probably too young to have it. Who already, I mean, you're 20, 25 years old, right? Yeah. Hopefully younger, right? Huh? Who knew the PS1? PlayStation 1, okay. Does the Atari 2600 tells you something? No, you're too young for that, huh? Okay. Well, the PlayStation 1 is still built of silicon technology. You probably noticed the big difference between the PlayStation 1 and PlayStation 4 and soon PlayStation 5 in terms of speed, graphic resolutions, right? By the way, I have a friend of mine who designed it in Sony. So I mean, I will have probably a couple of beers with him next week. Do you know how they speeded up the dimension of the speed of the PlayStation 1? By introducing actually strain. They strain the structure because actually it increases the speed at which the electrons are traveling between the source and the drain of your transistor. Well, problem being that you are at a certain moment, you cannot keep on stretching silicon as you wish it to stretch. And people have been trying to introduce germanium because intrinsically germanium was actually has a higher mobility. So why is this interesting? Because actually the current you get between your source and your drain, and I apologize, I hope you are not you don't all have a degree in electrical engineering, because I understood that the audience was somewhat homogeneous. So I'm just going to refresh your mind about how transistor is working and how you get current out of this. So in your current here, ideally what you want is to have the largest current you want in the system, okay? And actually it depends on a lot of different things. It depends on the thickness of the oxide you put to isolate it between the channel and the gate. So this is a Tox in the system. So people have been working in reducing as much as they could through time. But also there is another intrinsic ingredient, which is the mobility, so the speed at which the electrons or the holes are moving from the source and the drain. Okay? Why do you want to have more current? Simply because then you can increase the operation cycle of your CPU. Yeah? And faster it goes, the faster your CPU works in your system. So basically you want to have a material that has a very high mobility. If you compare the mobility of silicon, germanium, and then also 3.5, you see that basically germanium is a very nice guy, because I mean, you see the mobility of the electrons is about 2 to 3 times larger than the one of silicon, and the same for the holes. So that's a fantastic guy, actually. When in Bell they developed the first germanium transistor, they were completely right to do it. One of the reasons for which people haven't done it on germanium anymore was bound to the cost, because I mean the abundance of germanium is pretty low, and then we find sands everywhere on Earth, right? So that's way easier to build cheaper electronics based on silicon. But you know, we are back to the roots and trying to introduce back germanium. So when we started working on the first germanium devices, this is what we got. So normally, if you monitor the capacitance versus the voltage, a true transistor, you have an off state, you switch on, then you have an on state, right? And guess what we got? A flat line, meaning that all the current was going everywhere in the system, so the transistor was not working, right? So people at that time were naively thinking, look, with 40 years of transistor, of silicon integration in our back, germanium is going to be a piece of cake. And believe me, it has been a pain in the neck, and I'm going to remain polite with that. Okay, so very, very clearly the transistor is not working, right? So what people did was simply to replace the silicon by germanium in the transistor, At that time we were using hafnium oxide, we're still using hafnium oxide, in order to isolate the gate and, from the source, the drain, and our channel. Remember, so far everything, the PlayStation 1 to I think is silicon based. So it doesn't work, and one of the reasons is that, I mean, if you measure the current which is going this way, that's what we call the leakage current, we see that we have a huge leakage current. So there is something ongoing in the chemistry of the materials that actually we don't really control. So the first thing that you do is that then you check, your handbook of chemistry and say, okay, what did I miss in the system? Very obviously, you have a problem at the interface. I told you, the device is about between 65 to 80% of interface control of the system. So you probably have a problem of controlling what we call the germanium dangling bond or the silicon dangling bond in the silicon technology, which is basically making sure that all the bonds at the interface are saturated. You don't want to have an unsaturated bond because they actually contribute to the leakage of the system. So people have been developing a huge amount of strategies in order to control this amount of dangling bonds which is in the system. And I'm going to show you first what is wrong there, or at least how people thought that there would be something intrinsic to the materials, and then the strategy that they develop in order to make it work. Okay, bon. So I spent at least 10 or 15 minutes to tell you that all the simulations actually don't work on germanium, right? And I'm going to try to convince you that actually you can get some insight in that. So I will spare you the detail, but basically we've been cheating a little bit and we found a way in order to correct your band gap in germanium from the misery that you get normally with classical simulations where you see it's metal to something where basically you have the right band gap in the system, so 0.6 CV. So the very first thing, if I recall properly, when we started working on this, we were suspecting that the quality of the interface was very bad, and actually germanium oxide in itself was a very bad oxide. It was semi-metallic based on the oxygen composition. So if you want to get some insight there and how it looks like, normally you do these simulations. So you build a system which is periodic, which is germanium, then you get an interface with germanium oxide, with different oxidation state at the interface. So this is a suboxide, and this is an oxide that you get on top of it. And then, okay, simulate how the electronic structure should look like. If your germanium oxide is very bad, you should have something which is completely closed here, that is to say, a metallic band structure. Basically, what you observe is that in this complete stack, if you analyze an electron structure, you see that the system has nothing in the middle of your gap. Meaning what? That intrinsically, if the chemistry of your material is basically what you model, there is no reason for which the transistor that I showed you should not be working, right? This thing here should not happen because there should be no leakage. But perhaps simply that, okay, we miss something, right? That the chemistry or the quality of the interface is actually wrong. So the next thing that normally you do is look, okay, perhaps the model doesn't make any sense. So let's try to correlate this with basically what we have in terms of information. And actually what we correlate is that's basically the fractional of germanium oxidation state. So you know germanium can be bonded in contact with the oxide in 4 different ways. You have either no oxygen in contact, that's basically what you call germanium oxidation state 0, then 1 oxygen is +1, 2 oxygen is +2, so on and so forth, or 2 + 1. So normally the populations of what you get at your interface shows a quality that's a unique signature of your material interface. And this is something that you can correlate with XPS measurements. That's basically what you have done here. If you plot the oxidation state versus the fraction of germanium which is present in the system, then you see that the model actually is limiting very nicely the XPS measurements. So the model makes sense, right? So it could be something else, but it makes sense. Perhaps that the electronic structure of this is very different. So basically, using these atomistic simulations, you can simulate the evolution of your band gap. So you see in blue over there the electronic structure of your germanium. So you see no defect, nothing. Would you have something which is metallic, everything would be filled here. You should see signatures in the band gap. Then you get somewhat in your suboxide region, and you see that the suboxide region, so band gap slightly larger than the germanium one. And then you end up in your germanium oxide, also nothing wrong. Okay, so that cannot be intrinsic to the material. That's not an intrinsic problem that we have, but more process-related system. Okay. You see here that I'm going to try to use a little bit of XPS because it's extremely difficult experimentally to quantify the quality of an interface. And XPS, with that respect, is a very powerful tool because it will give you an idea about the chemical composition in the system, provided, of course, that you can simulate it. So we can do that, and we'll try to convince you that it gives you some flavor what's going on in the system. So how do we simulate that? Well, very similarly to how you would do it experimentally. That is to say that you work, in this case, this is the case of nitrogen, you work with a system that has all these electrons, and then you remove the core electrons from the system, you take the difference in energy between the system that has all these electrons and the one that lost one electron, and that gave you a unique signature. And this signature, basically, you compare it with respect to a reference peak that you want. So you know if it is more on the left side or on the right side and which energies. So does it work? Well, actually, we've been testing this on a lot of different molecules. And basically, I put it here, the shift in the 1s signature of nitrogen in different molecules versus what you compute versus what you measure experimentally. And you see that the peak is very sensitive to the chemical composition. If you have oxygen, if you have carbon, or if you have nitrogen main group, you basically tune a lot the position of your peak. And these simulations are able to capture it. So you have a way to validate your model. If you know that you have a certain peak shifted by, say, 3 or 4 eV experimentally, then you build back, you do some kind of reverse engineering, you build back your interface model, and you check if for your scenario the shifts are the same or not. If that's not the same, that's basically what you don't have in the system. We then apply that to the case of germanium oxide. Okay, and you see over there the devolution of the experimental peak versus the computed one. So you see that you are not doing too bad. That's not exactly one-to-one correlation. Why? Because experimentally, the peak that you get, and I hope I have an example here, it looks something like this. You see this big potato, and you need to figure out exactly what is the maximum of your peak, and there are always a little bit of deviations. In the simulation, you don't get this distribution of peaks, so that's slightly easier in a way. So you see that qualitatively we're good enough. The question is, okay, what could be wrong? Remember, in these devices, we try to integrate them in the same ways we would have done for silicon. That is to say, we put germanium and we put hafnium oxide in contact with it in order to have a low dielectric constant. Why? Sorry, a high dielectric constant. Why? Because this actually is appearing 2 times in your drive current, especially on the scaling of your dielectric thickness, in order to help boosting the performance of your system. You are still sitting in the same boat, or I'm crazing too fast for you? Still okay? Good. Okay, so starting from that, then you can say, look, perhaps this hafnium oxide, we can deposit on top of it, because it's never germanium hafnium oxide, it's germanium hafnate, so some kind of intermixing with hafnium oxide and hafnium oxide. Perhaps this guy here, this blue atom, which is the hafnium one, is doing something wrong, right? So then what you can do is basically you can simulate the signature of XPS, the XPS signature of your system, putting different atoms, different hafnium in different positions in coordination. +1, +2, +3, +4. In this case it's +4, which would actually simulate the formation of a germanium hafnate. And you see that you have a specific shift, which is very different than the germanium oxide. So you should find a very specific signature in your XPS spectrum. Even more important is to try to understand is if you have this guy close to the interface, does it generate defects in your band structure? And basically what you observe here is that there is no defect in your system. So this guy, if it is really correctly oxidized, is not doing anything. However, if it diffuses a little bit closer to the interface and start making germanium hafnium bonds, then what you observe in the electronic structure is that all of a sudden you see that this extra peak close to the bottom of the conduction band. So this is the top of the valence band, this is the bottom of the conduction band. You see your electron gap. Then you see an extra peak. And this extra peak is actually coming with the formation of a germanium hafnium bond here, and which is actually pinning your Fermi level. So pinning the Fermi level, meaning what? That normally your band gap is intrinsic. If you dope your system N or P-type, you can have your Fermi level located on the top of the valence band or at the bottom of the conduction band. If you have a defect, This defect actually contributes to the leakage current you have in your transistor, and is actually destroying the operation of your system. So what you observe there is that basically you have perhaps a candidate that can explain the leakage of your system, provided that you find the right signature using XPS. And you see that the specific signature here is very close to the one of germanium. It's just shifted a little bit on the left side. So my colleagues have been spending a lot of time in trying to figure out if they could find like these peaks. And this is typically how germanium oxide in contact with germanium or germanium hafnate looks like. So what you observe is basically you have two big peaks. You need to be able to deconvolute the XPS spectra. You see that, and you will have to believe me, I had to believe them, that in the convolutions they could find another peak which is present in the system, which is about 2.5 EV with respect to the germanium oxide bond. So 2.5 EV actually means that this could be this guy here, 2.5, 3 EV. Okay. Now what you're looking for is something that looks somewhere here, an alpha EV. Well, I mean, spent a lot of time having a look at the plot and never been able to find the peaks there because it's probably swollen completely in the distributions of the system. So what happens is that we think that the leakage is actually coming from the poor control of the quality of the interface generated with the germanium hafnium bond. We could actually never measure it experimentally because probably the concentration is too low to be physically accessible using XPS, but electrically we are probing it. So basically, we think that we have a problem of interface control. So how did we improve it? Well, we are going to step backwards and we're going to try to keep on working with silicon instead of germanium. So you will tell me I'm crazy because I mean I just started to explain you silicon, strained silicon, then we replace strained silicon by germanium, right? And then no, it doesn't work, then we go back to silicon. Well, we're going to try to take the best of the two worlds. In the sense that we will keep on working with germanium, but because we have problem controlling the quality of the interface between the germanium channel and your dielectric, we are going to use a little bit of silicon on top of it. Not much, huh? 1, 2, 3 monolayers. Because that's an interface that we know how to control it. So what actually we observe is that basically we have the first world record dynamic of a working germanium devices. So just to show you here, this is a silicon-silicon oxide behavior, and then all of a sudden we see that the performance is improved, the leakage current was going on, and you see that mobility was shooting up. So that worked. All this is very nice because we see an improvement in the system, but we also observed a list of annoyance. And the list of annoyance is that the PowerPoint sketch that I showed you is basically this very nice germanium silicon control interface, but in reality, if you measure the compositions of germanium and silicon using toxins measurements, so secondary ion microscopy measurements, so you monitor the evolution of the ions generated by bombarding a surface, and that gives you a composition analysis. You see that basically, if you plot the thickness for different thickness of silicon, you see that there is a lot of germanium in diffusing in the system. So this is very different than that. So back to square one. How can it be that we don't control this very sharp interface? And then how is this going to impact on the system? So the benefit whenever you're doing simulations is that you can do a little bit crazy things. You can make different scenarios. And in order to try to basically understand how your process conditions are impacting on the chemistry which is present in your materials, you can actually say, look, I can try to build a silicon layer which will be on top of my germanium, and I will assume that I just put a block of silicon in my system, okay? And then I will heat it up in the same conditions as I would normally. I will even speed it up just to try to see if I can observe germanium diffusion in my system. Or what you can do is you can build layer per layers. That is to say that you will put one monolayer of silicon in the system. So normally we use silane, which is a chemical precursor in the system. So you simulate the process of the reactivity, you stop, you remove the hydrogen, which is abundant in the system, you put a second layer, and then you start monitoring the system to try to understand if you can capture this diffusion in the system. That's basically what we have done. And we'll call this the layer per layer growth. So one layer of silicon, we heat up, we remove the hydrogen, we put a second layer, so on and so forth. Or one step, we put everything on top of it, and then we see what's going on. So when you do these simulations, it looks something like this. This is your germanium surface. You start bombarding with silane, and then you need to be patient. So that's day drop gems, job. Sorry, that's a dream job. I will make it. Because I mean, we had to wait 1 month to get something getting out of the computer. So okay, we are busy with other stuff. But I mean, 1 month later, typically you get morphologies that look like this. So the pink one is the silicon, and the green one is germanium. So what you observe is that sometimes you get a little bit of germanium diffusing in the system, with the white atoms are basically the hydrogen present in the system. So once you have this, then you can try to evaluate the germanium segregation. So I'm reporting the germanium to silicon ratio versus number of layers, so the positions in my stack. Basically, I'm moving from this part here. So here it is pure germanium, so it will be 1, 1, 1, 1, 1, 1, and then here I'm getting a little bit of silicon germanium, deeper and deeper, then it will be silicon richer. That's basically what I observe here. So if I adjust my starting surface, I have a sharp interface here, which I see that after 5 atomic layer deposition in 1 step, so just silicon deposited, I wait and I collect what I get. What I observe is that the germanium composition is going down, the silicon composition is going up. I have quite some intermixing in the system. Now if I make it layer per layer, so 1 layer of silicon, I remove the hydrogen, I go for the next step. What you observe is that there is a difference in the intensity of germanium, which is present in your system. You see, you have a larger peak here than what you have normally here. And actually, if we extract for different thicknesses of silicon the evolution of the germanium-silicon ratio in this region, and you measure it and you compare it to the experimental data, you see that you have qualitatively the same trends. So basically, it means that there is a difference between this process and this one. So there is some kind of segregation mechanism. And actually, the segregation mechanism is actually driven by the presence of hydrogen. So when we deposit, that's the process we typically use for the deposition. This is called chemical vapor deposition. So we use silane present in the system, or trisilane. So depending on the type of precursor we have, and the temperature we have, we can either keep the hydrogen on top of the surface or not. And it turns out that basically, if you have hydrogen terminating the surface, you tend to keep the silicon on top, because the system is about 0.2 eV per diameter of your surface reconstructed, more stable than the situations where the silicon will diffuse in the system. While if the temperature is too high, you're going to dissolve your hydrogen present in your system. Basically what you get the germanium diffusion in the system, where germanium is more stable than in this case for silicon. So all of this, it was done 7 or 8 years ago, prompted the discussion internally in IMEC to try to reduce this working deposition temperature. Now we have been able to reduce the temperature depositions to something around 300 to 350 degrees C, switching to different chemical precursors. So in practice, one of the reasons why we had good performances but not the best was coming from the fact that we don't have a correct control of the chemistry of the materials and the up diffusion we have in the system. So instead of having a very nice block of silicon and germanium like this, we have silicon germanium with uncontrolled amount of germanium in the system. Okay, I mean that's a little bit a long story, but to tell you that we started from something that looks like this to something that now looks like this, that is to say a working transistor. Okay, we still have a lot of dispersion, meaning that we don't have still very functional devices. We still have a lot of defects present in the system at interface, but it works very nicely. So what do you want to do? Do you want to have a break now? Or do you want me to continue to be done earlier? Who wants to have a break?
Break.
Okay, go. So let's take, what? 5 minutes? Is that okay? No? So that we don't finish too, it doesn't take too long and you can go for lunch also. 5 minutes, so we resume at 12? Okay, thank you.
Does not look like your case. It's too small. It's too specific. It's a lot of entry. Yeah, actually, last BDW, not this BDW, I just presented like how the voice we create by the particles in the interface. Yeah, I just provided some results in the case of the practical. I just this is a wafer, and I deposited one small part on the wafer, and I just do the bonding. I did the bonding, and I see the voice. Induced by the particles. And I changed some dimensions of the particles, like larger particles, smaller particles, circular particles, and then see the how does voice look like bigger or smaller, or there's some rectangular or something, different shapes. And yeah, this is a practical. Yeah, this is experimental research. And also in another way, I just try to simulate by using the mark. But I think a mark was not working. Did not working well because the mark simulating like one dimension, like classical sectional, or something, three-dimensional. So finally, I didn't provide the results. Yeah, I just tried using the mark, but actually, what I wanted to simulate by using the mark is like a wave propagation, like yeah. Actually, the voice, how the voice will be, for example, this part. You know, if you put something on the surface, maybe the propagation wave is coming like this.
Probabilmente dai, su, magari stai zitta.
Maybe if you imagine that this one, this screen, if you put this projected screen, maybe if you have a purpose here, maybe the bonding wave.
Sicuro è difficile invece.
Bond wave like this. Goes around the particles, and finally by each other. Finally, by this particles, the unwanted areas what exists around the particles.
Yes. Well, I mean, I'm organizing it in dynamic, of course.
We see the interface.
Well, it's typically outside, so you're doing a master test there.